Okay, so now we know what are some of the potential problems. Now the next question, of course, is how do we fix this? So what are the different mitigation techniques that we can use to prevent someone from spoofing the router or from replying with illegitimate DHCP requests or just pegging the router CPU? Now, when you look at the actual implementation for this, at least within the scope of Cisco's implementation, which is what we're looking at here today, a lot of these features are only available on the newest possible code trains for the newest possible platforms. So in the case of the Catalyst switches, a lot of these are going to be in the 15.2 Catalyst code, the newer iOS XE switches, and then in some of the little bit lower 15 trains, like 15.0 we're going to be looking at today. Some of these mitigation techniques are there, but not all of them yet. So if you're thinking about doing an IPv6 implementation and you haven't yet, that's one of the big considerations that you have to think about. You know, what do my switches support code-wise in terms of these security techniques? Because if you implement it without thinking about it, it's very, very easy for someone to actually turn these attacks on, and then have potentially very, very devastating effects. So let's look at here the Cisco documentation. So let's go to the documentation page. Actually, let's just go to Cisco's main page to start here. From here, we're going to go to support. Then we're going to go to configure all the way at the bottom. And the platforms here specifically are going to be the LAN switches. Now, when we look at this this high-level network overview, as I mentioned, there's basically 3 different places that you could mitigate these type of attacks. You could mitigate them on the end hosts by doing, let's say, static neighbor discovery entries that I know the router 1234 has the MAC address ABC. But the problem is that really feasible to implement that and to manage that in the network? So if we have tens of thousands or potentially hundreds of thousands of hosts or servers, quickly that's going to get out of control. So you theoretically could mitigate these attacks down here at the victim, but in most cases that's probably not feasible. Okay, then as we go to the upper layers in the network, the cabling of the end devices is probably going to be aggregated together from the access switches or up to the distribution switches. So this would be another potential point where we could do mitigation, is going to be the first switch or the distribution switch, maybe where the layer 3 gateway is in the network. Then going further up the stack, we could say on the router, before you send your packets out to the WAN or before they come back in, we could potentially mitigate some of these techniques there. But in today's examples, we're mainly going to be looking at these two. So what could we potentially do on the router? What could we potentially do on the switches in order to prevent these type of attacks? So first, let's look at this from the switches point of view. So under products, we're going to go to switches, LAN access switches. So campus LAN access. And let's say I want to say 2960X has this documentation. Yeah, 2960X. Okay, so here let's go to configuration. And let's see what's the newest version they have. They have 15.02. Let's try here under security. Then here, configuring IPv6 first hop security. Now, if you're familiar with any of these other techniques that are used for IP version 4, for layer 2 security, a lot of them carry over pretty similarly to IP version 6, things like the IP Source-Guard, dynamic ARP inspection, and the DHCP snooping for IPv4. The basic theory of those is going to carry over to IPv6, but we'll see from an implementation point of view, it's a little bit different how you would specifically turn these features on. So under here, under first hop security, the techniques it's talking about here, you can do IPv6 snooping. You could do neighbor discovery inspection. There's a feature that is the router advertisement guard. the DHCP guard, and then the IP source guard. Now, without even looking any further into the specific documentation of, what is this, how to implement it, you can kind of pretty much predict based on just the naming convention where can these techniques be used to mitigate the attacks. So the router advertisement guard, this would be to stop someone from spoofing that they are the router. So this is going to prevent the man-in-the-middle attack where you send traffic out onto the LAN, someone else intercepts it because they say, I'm the router, but in reality they're not. The DHCP guard, obviously it's going to be for DHCP. So when we send the requests out, we want to make sure that the response comes back in from only the legitimate server and not from any other attackers on the LAN. Some of the other ones here, the source guard, this is going to be used to filter essentially in the data plane the packets based on the IP address and the MAC address pairing, where something like the neighbor discovery inspection, the router advertisement, and the DHCP guard, these are filters of the control plane, where the source guard would be a filter of the data plane. So some of them are working on the protocols behind the scenes, like neighbor solicitation, neighbor advertisement, router solicitation, router advertisement. Then something like source guard is going to be on a per packet basis. Every time it's something in the data plane actually comes in, I'm going to do some sort of hardware check against this and say either yes or no, is this packet legit? If so, admit it. If no, then drop. So before we get into the specifics of these, let's talk about them from kind of more of a high-level overview. The router advertisement guard is going to be to protect against when the hosts are dynamically discovering their default gateways. So we send the router solicitation out from the end host. The router is going to advertise, what's my address for the default gateway. So router advertisement guard is going to fix that problem so someone cannot spoof the default gateway's address, and also to stop them from spoofing the stateless auto configuration. So both router spoofing and prefix spoofing. From an implementation point of view of the Catalyst switches, you can apply this either at the VLAN level, so it applies to all devices in the LAN, like VLAN 100, or you can apply it to individual ports. Likewise, the DHCP guard is going to prevent against someone spoofing the server. Again, the difference between IPv4 and IPv6 DHCP, one of the key differences is that the DHCPv6 server does not assign the default gateway. So this means that the DHCP guard is going to be used to prevent someone from spoofing the server's range, like the prefix range that they would allocate, but it doesn't prevent against someone spoofing the router. So the default router here, as the second bullet point says, default routers learn through stateless auto configuration from the router advertisement messages. So you normally would want to run the router advertisement guard and the DHCP guard at the same time because they're different vectors of the same type of attack that someone is either trying to do denial of service or man in the middle. So normally you want to turn both of these on at the same time. Now the other one, the IPv6 snooping, is going to be where the switch in the middle is going to figure out from the neighbor solicitation and the neighbor advertisement messages what is the correct IPv6 to MAC address mapping. And this is very similar to in IPv4 what we have is dynamic ARP inspection. So the switch in the middle is listening to the control plane messages, which is the neighbor discovery protocol, and it's also going to listen to the DHCPv6 messages. Now, when the neighbor is saying, my IPv6 address is 2001::1, my MAC address is A, the switch is then going to learn that and put it into this snooping table. Then when the DHCP server assigns the prefix, the switch is already going to know what MAC address is in the snooping table, and it's going to be able to make a correlation between these. So the idea is that the switch is now going to be able to track the neighbors and figure out which hosts are supposed to be on which ports. So it's going to prevent someone from spoofing another host on the segment. So you won't be able to do your gratuitous neighbor advertisement and take over somebody else's MAC address. But normally you would also want to run this with the router advertisement guard and the DHCPv6 guard again at the same time because they're different vectors of the same attack. So they're kind of related, but you generally would want to turn all of these features on. Now, the other thing that you would need to do when you're using this feature is to make sure that the switch knows, are there any devices on the segment that have static addresses? Where in most cases for IPv6, probably the only static address is going to be your router, but maybe you have some servers on the LAN that have static addresses, or maybe like a printer or something like that. If that's the case, the switch is going to need to know what is that correlation between the IP address and the MAC address, because if it doesn't receive the DHCP messages, then it's not necessarily going to know which one, what these particular mappings are. So again, technically there's separate features. When you turn snooping on, it's implicitly turning on the router advertisement checking and the DHCP guard. So programmatically behind the scenes, it's multiple things that it's doing. But when you look at it from a syntax point of view, you basically turn one on, and then it's also going to turn the other ones on as well. Another way is, like I mentioned, the IPv6 Source-Guard. This is going to be a filter, again, in the data plane, not in the control plane. And that's the difference between these first three, where they are control plane filters. This last one here, this is a data plane filter. So this is going to be similar to IP Source-Guard for IPv4, but the key is that in order to do this, you need to have that database that creates the mapping between the IPv6 address and the MAC address. So in other words, when the host comes onto the segment and asks the router, what's the prefix I'm supposed to use? Okay, the router says your prefix is 2001/64. The end host says, okay, I know the prefix, I'm going to generate my own end host address based on my MAC address. Once I have those, I'm going to send the neighbor advertisement telling everybody else this is the address that I generated. The switch in the middle, assuming it's running snooping, now knows the correlation between those two pieces of information. What's the IP address and what's the MAC address? And then when we go to enforce the actual filter, the switch can say when packets come in on that port, they should only come from IP address 2001::A, and they should be coming from MAC address ABCD, because we already knew based on that database what the binding was. So in other words, it's basically creating an automatic access list, but the key is it's doing it based on the neighbor binding table. So if you want to use this feature, you would either have to do static bindings, or normally you just run snooping in conjunction with it. Now, technically, there is another way that has been proposed to do this, something that is called Secure Neighbor Discovery, or SEND. Now, the potential shortcoming of this implementation is that they said, okay, we know that the messages are in clear text, and that's the problem to begin with, that someone sends a solicitation and everyone on the LAN segment can hear that because it's going to the all host, it's going to like the broadcast address. Or when the router sends the advertisement, we can read in clear text what the router is sending. So they said, well, why don't we just authenticate that data? Let's add some sort of crypto to it, so when the router and the end host are talking, they know that this is actually an authorized router on the segment. It's not someone that is trying to spoof them. Now, the problem with this is you can imagine is that you would essentially have to introduce PKI onto the last hop segment and have the routers enroll with a certificate, and then have all of the end hosts to trust that particular certificate. Because the key in this attack is not that the end host is illegitimate. The attack is that someone is saying that the router is illegitimate. So the router would say, here's my crypto data, my keychain is, ABCDEFG. When I send you a neighbor advertisement message, and when you send me a router solicitation, those are going to be authenticated between the end host and the router with PKI. The problem with this, though, as you can imagine, means that you're now moving your mitigation technique down to the end host. So if you add a new router, you have to generate new certificates, and then potentially install that certificate in hundreds or thousands of end hosts, depending on what your underlying network design on the segment is. So theoretically, you could do it this way. Because there's an extension basically in the router advertisement to include the certificate, but it's not really implemented yet. A lot of the end host software like certain Windows versions, certain Mac OS versions don't yet support this. So it is potentially a solution, but in my opinion, it's not really going to be a valid solution because it would be too difficult to manage unless you're already doing PKI to every end host and you have some, maybe large-scale auto-enrollment process or something like that. So it is potentially there that you could do it, but is that really feasible? Not really 100% sure there. Okay, so let's take a look at a couple of these techniques and see the end result of them. So if we look at, let's say, the IPv6 snooping policy. Okay, the configuration of this is pretty straightforward. You say in global config that I need to create a policy that's going to specify, what am I actually doing in the snooping. So you can say, what protocols do I want to inspect? Do I want to inspect DHCP along with neighbor discovery? We can give a limit on how many addresses could exist on that particular port. So maybe you're looking at this, you're on the LAN switch, but attached to that LAN switch is a wireless access point. So the wireless access point is bridging multiple MAC addresses in, so you might need to allow multiples there. Or maybe you have your end host plus an IP phone. So you have two MAC addresses on the port, and you might need to allow more than one in. So it's similar to how like port security works, that if you needed multiple addresses on the segment, you could say, what's the limit of addresses that you can specifically configure there. So as you can see, compared to the IPv4 counterparts, if you're familiar with DHCP snooping in Catalyst, this is a little bit more complicated from an implementation point of view. And I'm not sure if they actually show the final example of this. So they said you can either attach it to the interface or you could attach it to the VLAN. And let me go back to the top. Let's see if they have an example of these. Not really. I think it's just how to configure. Then the neighbor binding table. This would be if you need to statically configure a mapping. So let's say you have a printer or some server that's on the segment, and you need to make sure that the switch knows that when they send their traffic in, that they have this IP address and this MAC address, because we're going to use that for filtering in the data plane. So this would be like configuring a static IP Source-Guard entry in Catalyst. It's similar to that, and you can see there's a lot of other options that go along with this versus the IPv4 counterparts. The router advertisement guard is a little bit, well, actually not a little bit, it's actually a lot more complicated than just the DHCP snooping in regular IPv4, and then also the dynamic ARP inspection and the IP Source-Guard. Essentially what you need to do in order to get this feature to work is to specify what is the link local address that the router is going to be sending the advertisements from, and then in the payload of the router advertisement, what is the prefix that it is going to be advertising, because otherwise the switch is not really going to know what's the legitimate router and what is a host-facing port. So essentially what you would say here is what is the port's role? So is the port going to an end host? Is it going to the router who's supposed to be sending the advertisements, or is it going to another switch? So if you have, maybe you're doing this in the distribution layer, you would say, these southbound ports go to the switch, then the northbound port that's going to your layer 3 device, you say that's where the router is located. That's going to tell the switch, which links should have the router advertisements coming in, which links do not. Then for the DHCP guard, it's going to be similar, that you specify when I'm looking at the port, which one goes northbound and which ones goes southbound. So if you have your DHCP server somewhere north in the network that's a central location, the switch needs to know if the DHCP offer comes in that way, that's the legitimate port that it was supposed to come from. But if it came from southbound where your end hosts are, then it should be discarded. And that's what it's talking about with the device role here. So in other words, the host mode and the client mode, so the host mode for router advertisement guard, the client mode for DHCP Guard are going to drop what would normally be the router's messages or the server's messages, respectively. Okay, then to do the data plane filter one, which is going to be the, let me go back to the top, which is the IPv6 Source-Guard. This pretty much you just turn this on. So they're saying we have a policy that is denying global auto configuration. It says denies data traffic from auto-configured global addresses. This is useful when all global addresses on the link are DHCP assigned and the administrator wants to block hosts with self-configured addresses to send traffic. Okay, so what this means is that when a host joins this segment, like I was talking about before, it sends the request to figure out who are the routers and what are the prefixes that the routers own. Normally when the router replies, the end host is going to say, take that reply with the prefix, generate an end host address, those two together, that's my global address. But in the case that you're using DHCP, the router is not the one who's supposed to advertise that, the DHCP server is. So you could say, like in this case, don't allow anyone to use stateless auto configuration. They must get their address allocations from the DHCP server, and assuming we're doing DHCP snooping for v6, then we're basically like combining multiple layers of security together. Okay, then you can attach the policy to the interface. So again, this is essentially the data plane filter. Okay, so let's take a look at the topology that we're going to be using. It's essentially the same type of logic as what I was talking about here with the end host. So we have 3 devices on the segment. Router 4 at the top here is essentially going to be what's supposed to be our default gateway. Then we have some other end hosts. We're going to say that router 5 is essentially the victim, and router 6 is the attacker. And then we have a switch in the middle, switch 3. This is where we're actually going to enforce the policy by configuring these different types of snooping. So first, let's go ahead to the routers here, and let's quickly again review what are the states that these devices need to go through before they can actually send their traffic onto the segment. So if we look at the config here, there's a very, very basic config that I have right now. So essentially all of these links here, Fast Ethernet 0, these are the links that physically go to that switch. So on the switch here, you can see the output of show CDP neighbors. It says routers 4, 5, and 6. These are attached on the remote sides on Fast Ethernet 0. So router 4 here's on port 1, router 5 is on port 2, router 6 is on port 3. So basically just 3 routers plugged in physically to this, this one switch in the middle. Okay, if we look at router 4, it says that I have a link local address manually assigned. Okay, where in most cases you normally wouldn't do this. You would just have the router or the end host generate its own link local address based on the combination of the prefix FE80 and then its modified EUI64 formatted MAC address. Okay, but in this case we're doing it statically. We're also configuring an IPv6 address, a global address. Now if we also look at the show run section IPv6, this router globally is saying that IPv6 unicast routing is on. Now the combination of this command that IPv6 unicast routing is on and that we have a manual global address assigned means that this device is now going to start sending router advertisements or responding to router solicitations with the advertisement saying that I'm the gateway. So they would say if you want to route traffic out, use 2001::4, which is my static address. And it's also going to say the prefix that you should use for stateless auto configuration is going to be 2001::/64, so the global prefix that is assigned to that particular segment. Now on the other devices, so for right now I'm on router 6. I'm simply going to shut this port down to simplify the topology a little bit, where we only have these 2 routers on the LAN. We have the router, which is 4, and then we're going to have the end host, which is router 5. So let's on router 5 here, we're going to debug IPv6 neighbor discovery. Okay, this is like saying debug ARP for IPv4. And let me make sure logging is on. Terminal on. Okay, we're on the console. So on router 5, we go to the LAN segment, and let's simply say IPv6 enable. Okay, so we're just turning the protocol on. Now, if we look at step by step the workflow it's going through, it says that first thing that happens is that we are requesting, let's see here, on fast Ethernet 00. We are trying to figure out this link local address that we generated, is this a unique address? So this is through the duplicate address detection request. Now specifically the way that this is done is that we're going to send the neighbor solicitation to figure out, does anyone else own this address on the segment? And if we were to look at the show interface fast Ethernet 00 and look at the MAC address, so let's say include that burned in address. If you look at the format here, it's 001C, F6, etc. And you look at the address that it shows, it's basically a variation of this, where it flips one of the bits here at the top that's called the universal local bit, and then it pads in the middle FFFE. So this here essentially is the end host address that router 5 chose. Okay, so it chooses the local address and it asks the other devices, does anybody else have this? Okay, it waits a certain amount of time and it says, okay, nobody replied, so my address is unique. I'm now going to send an advertisement to everyone else saying, I now own this address. And if you were to actually do a packet capture this, inside the neighbor advertisement, you would see it's saying, this is my IPv6 address, and this is the MAC address that that it is bound to. So basically, it's like a gratuitous ARP reply. Okay, the next thing that it needs to do is to start listening for the routers on the segment. Now, in the case of the Cisco iOS implementation, it's a little bit different than you would see from like a Windows host or like a Mac OS host, that it doesn't automatically listen for the stateless auto configuration as an end host. If you wanted it to get an address through that, you just need to say IPv6 address is autoconfig. Okay, and then you would probably want to do a default route to whoever the default gateway is. So if we look at the debug now, it says, I'm sending a neighbor solicitation. I'm trying to figure out who are the routers on this segment. And the end result is that we got a router advertisement from FE80::4. Okay, again, that's the address that I had configured on router 4. So 5 learned about 4, says, okay, I'm going to use this neighbor as my default gateway. So I'm installing a default route to them. And then it actually doesn't show here. I'd have to do another debug. Let's say debug IPv6. There's a separate debug, I think, for stateless auto configuration. ICMP. Debug IPv6 address. Let's try that. Let's shut the link down and then bring it back up. Or actually do this. No IPv6 address autoconfig default. Okay, so we can see it received the router advertisement from router 4. And here it is. So it's saying inside the router advertisement that 4 gave to us, router 4 said the prefix you're supposed to use for stateless auto configuration is this one here, 2001::/64. So it says, I'm now going to take that prefix, I'm going to generate a unique end host, so based on my MAC address, and then when I do that, I'm then going to send a neighbor solicitation saying, does anyone else have this address? Okay, so we're going through duplicate address detection. You can see it also joins this solicited node multicast address, which is basically for the duplicate address detection. Then it says nobody replied. Okay, so my address is unique. I'm now going to send a neighbor advertisement saying that this is my unique address. So if we were to go to the router now, router 4, and look at the show IPv6 neighbor discovery now, show IPv6, let's see, it's the equivalent of the show ARP, show IPv6 neighbors. So we now know that this link local address corresponds to this particular MAC address. So like if we looked at the switch and looked at the CAM table to find this MAC address, you'd see that that this is talking about router 5. Now on router 5, if we look at the show IPv6 interface and look at the details, you can see it says that IPv6 is on. This is my link local address that I generated. The prefix that router 4 advertised to me is 2001/64. From this, I appended my EUI64 address, and then I joined the solicited no multicast address. This is for duplicate address detection. Okay, it also says I'm listening for the all host multicast. That's like with the all 255s in IPv4. It also says that there is a, let's see, there's a lifetime for the router advertisement. And somewhere in here it says the default router is router 4. And then I think on router 4 side it shows the priority. But the key being here, now if we look at the show IPv6 route, essentially router 5 knows to send the default traffic to router 4. So it's basically acting as an end host. Normally the router is going to act as a router, not as an end host. But by saying on the interface that we want to do that auto config. See, my connection's lagging a little bit here. And there's a question here, is the IPv6 enable command required? Technically, no, it's not. What this does, if we scroll back up to router 5, this one here, what this does is basically tell it just to negotiate a link local address and not to assign any global addresses. Technically, it's a valid design that the router doesn't need a global address because you're never routing traffic to the router, you're only routing traffic through the router. So there could be some certain circumstances where you can run a routing protocols just with link local addresses. Like you can form a BGP peering with your ISP and use just a local address. Then it means you're not vulnerable to anyone doing some sort of remote attack onto that segment. Because FE80 is a non-routable address. It's link local by definition, so it means that no one would be able to send you packets. But normally you don't need to use that command because you would just specify the IPv6 address, either the global address or autoconfig, and then when you do that, it automatically generates the link local address. So we could take this off now, and it's still going to work fine. Okay, so my connection flapped for a second there. Let's look at router 5 now and look at the show IP route IPv6, or show IPv6 route. Okay, so we can see it has now the static default route that's pointing towards router 4. So on router 4, if we look at the show IPv6, let's see, interface F00 prefix. This shows what the prefix is that we are advertising in the router advertisements. So it's 2001:/64, and then what is the what's the specific lifetime? So when does this eventually time out? But again, the problem with this LAN segment now is that there's nothing preventing some other router from coming onto the segment and advertising itself as the valid router. So let's say we were to go to router 6 and do the same thing, that we go to this link. And actually, to make this a little bit clearer, let's do this. Let's not put it on the same network. Let's put it on a different network. Let's say the IPv6 address is 2002:/64. Okay, then on the end host, which is router 5, let's shut the interface down there. and bring it back up. So let's see what happens once router 5 generates its local address and then sends the router solicitations. And we're basically looking at looking for what are the RAs that came back. So it says we got an RA from router 4. But we also got one from 6. I'm not sure where it shows it in here. It should be FE806. There it is. So received a router advertisement from 6. If we look at now the show IPv6 interface faster than at 00, notice that we have 2 different addresses assigned. We have not only 2001/64 that came from router 4, but we also have some other prefix 2002 that's coming from a different device on the segment. So we don't necessarily know now when we use the router as the default gateway, which one are we going to pick? Are we going to pick router 4 or are we going to pick router 6? Now, one thing we do know is that if we are doing specific routing to 2002, this traffic would go to router 6 because that's directly connected on our segment. Even if we were to receive an IGP route or a BGP route for 2002 from router 4, simply based on the administrative distance of the connected link being lower, we would prefer router 6 for those destinations. So in other words, the other router on the segment, so the attacker can basically poison the routing table by sending multiple router advertisements with different prefixes, and then you would be forced to route those prefixes directly to them. So let's actually take a look at the routing table. I'm not sure what the result is going to be here because it depends on the order that the advertisements came in. So in this case, look what happened. It says our default gateway is 6. So even though we do have global addresses that are assigned on multiple prefixes, so what happened is that router 5 came up, it sent the router solicitation, router 4 said, in my router advertisement, use 2001/64. Okay, then router 6 said, use 2002/64. So for whatever reason on router 5, probably based on the order that the packets came in, it assigned an address 2001. So whatever plus whatever the EUI 64 address is, but then it also installed 2002/64, and it said now my default gateway is 2002::6. So essentially all packets that are leaving this segment are now going to go from the victim to the attacker first. Then router 6 could rewrite this. It could do like an IPv6 NAT to rewrite it to 2001::6, and then send the traffic in that direction to the gateway and then out to the rest of the public network.